Okay, so now we're doing 10 and 11. Okay, what type of bond is expected to form between N and O? Well, N and O are both non-metals. Looking at the periodic table, we're looking at the people, in the corner over there. I mean the elements. Okay, so two non-metals, that's going to be a covalent bond. Answer A. Okay, what type of bond is expected between lithium and iodine? Well, lithium, is way over here, and iodine's way over here, so it's a metal and a non-metal. So that's definitely ionic bond. Which type of bond is described as a lattice of positive ions in a sea of electrons? We are talking about a metal, okay, and all that sea of electrons is what allows metals to conduct electricity and be malleable and ductile. Okay, which compound represents an ionic compound? Well, certainly not that one. That's two nonmetals. That's two nonmetals. That's two nonmetals. It's potassium iodide, a metal and a nonmetal. All the following form covalent bonds with bromine except, okay, remember that covalent bonds are two nonmetals. Okay, so who doesn't? It's the metal. There's potassium. Potassium's a metal. The other three are all nonmetals. They will make covalent bonds. Okay, bonds of which of the following elements is expected to be the most polar? Well, if you look at these are all nonmetals, nonmetal, so they're all nice covalent bonds, but we need something that is from the strong nonmetals and the weak nonmetals. So one here and one there, that'll be a polar. So not C and H, those are both weak. Not N and O, those are both strong. Okay, P and F, that's a good one, because here's F as a strong nonmetal, P is a weak nonmetal, and S and B are both weak, so that won't be either good. So answer C. 62, the Lewis symbol for carbon. Okay, carbon is in the fourth column, fourth family. It's got 4 dots. It can make has 4 valence electrons. It can make 4 bonds. The Lewis symbol for oxygen, 2 minus. Okay, if we were doing neutral, it would look like this. Okay, but if it's 2 minus, it gets 2 more electrons, and so it has 8 dots. The correct Lewis symbol for aluminum. Okay, aluminum, has 3, so we're going to put 3, 1 on each side. So that's got too many dots. They're the wrong pattern. There it is, right? Answer A. 65. Each of the following describes ionic solids except. Okay, so we're going to knock off anything that does describe an ionic solid. So be careful about these excepts on tests. They are formed from metal and nonmetal. Yes, they are. That's not the answer. They conduct electricity when dissolved in water. Yes, they do. Also when they're melted. They have a sea of electrons. No, we're talking about metals now, so this is the wrong answer, and D can't be the right answer. So C is talking about a metal. Properties of metals include, okay, brittleness, no, okay, because they're very malleable and ductile. Dull surface, no, they're shiny. Poor conductor, no, they're good conductors. Poundable into sheets, okay, that means malleable. Malleable means pounded into sheets. The element would be the best conductor. Okay, well, an easy one here is if we have a metal and some nonmetals. Okay, arsenic's a nonmetal, phosphorus, sulfur. There's tin. Tin is a metal. So if you know your elements, you know that Sn is tin, from the Latin word stannum. 68. Which of the following describes the bonds in a molecule of ethine? Okay, well, carbon has 4. Carbon can make 4 bonds. Hydrogen, okay, can make 1 bond. So we'd make a bond there, we'd make a bond there, we'd make a bond between, and these other 2 are going to have to make bonds as well. So we're going to have a triple bond. So which of the following describes the bonds? Well, it looks like we have 2 singles and a triple. Okay, a triple bond and 2 singles. There it is, answer B. So the idea is draw the picture and then answer the question. 69, the total number of dots drawn in the Lewis structure of nitrogen. Well, nitrogen, N2, okay, each of those has 5 dots, so we have to have an answer that's 10. No matter how we draw this, it's going to have 10 dots, and it's a triple bond between those 2. 70, in the Lewis structure for ammonia, how many lone pairs of electrons does nitrogen have? Okay, nitrogen has 5 valence electrons. It's going to hook onto a hydrogen, it's going to hook onto a hydrogen, it's going to hook onto a hydrogen. Okay, so where's the lone pair? Right there. There's 1 lone pair in an ammonia molecule. Okay, which of these molecules is polar? Okay, polar. Anything that looks really even is not going to be polar. So that's very even. That one's very even the 2 ways. This guy, if you think about it three-dimensionally, we saw our model in the classroom, that one is going to be very even. It's this one, this is the answer, okay, because nitrogen with that lone pair on that, then it causes this other to be off to one side, and because of that, this guy is going to be a polar molecule. The bonds will not cancel. Okay, water molecules are attracted to each other with this type of intermolecular force. Okay, so when I've drawn a bunch of water molecules, okay, and so the blue part here, these are covalent bonds between the oxygens and the hydrogens. So all these are covalent bonds, and that's not what we're talking about. We're talking about intermolecular forces, so what's going on in between the molecules. So I drew those with the dotted lines, and so my answer here is hydrogen bonding. Okay, hydrogen bonding, where the hydrogen is covalent bonded to one oxygen and attracted to the other oxygen. That's called hydrogen bonding. Okay, which of the following is incorrectly paired with the solid? So we're looking for ones that are correctly paired, and we're going to knock them out. Okay, bronze, that is a metal. Okay, bronze is a mixture of tin and copper. Okay, CaO, that's a metal, non-metal, that's ionic. H2O, that's molecular. Okay, the answer is this one, P4O10. Okay, network covalent solids, there's only 3 of them. Okay, carbon is diamond, carbon is graphite, and SiO2. Those are the 3. So P4O10, that is a molecular solid. Okay, number 11, properties of gases. What is true about a sample of gas molecules according to the molecular theory? What's true? So 3 of these are not going to be true. At high pressure, molecules collide against the walls of the container with the same frequency. No, at high pressure, they're going to collide more often. Every gas molecule in a sample travels at the same speed. No, they have the same average velocity, but they all have different speeds. Some are going fast, some are going slow, and that kind of stuff. See, the volume of the gas molecules is negligible. That's it. We were saying that the molecules are just kind of like little, mathematical points. They don't take up any room. And there are significant attractions between polar molecules, okay, not in a kinetic molecular theory of ideal gases. So there would be no IMFs. Okay, 75, a rigid container, which means the volume doesn't change. What increases as the cylinder is heated? Okay, so the volume's not going to change. What's else going to happen? The average kinetic energy of the sample, yes. If you heat it up, then the average kinetic energy will go up, so that's true. The number of collisions the gas makes with the walls of the container, certainly. If they're moving faster, they're going to bump into the edges harder. The number of gas molecules in the container, no. Okay, if it's a rigid container with no leaks, then the number of gas particles stays the same. So 1 and 2 only. Answer B. Okay, for 76, 2 balloons are filled to 2 liters at 20 degrees. One is filled with helium, while the other is filled with hydrogen. Okay, one is filled with helium, the other is with hydrogen. If the pressure exerted by the gases in the balloons is the same, what can we conclude? Okay, so we have equal pressures, we have the same volume, we have the same temperature. Okay, so they must have the same number of particles inside there to be able to do that. So the masses of the gases is the same? No, because they have equal numbers of particles, but this one weighs 2 AMUs, this one weighs 4, so the mass is not going to be the same. The number of particles is the same, yes. It's called Avogadro's hypothesis. Equal volumes at the same temperature and pressure have the equal numbers of particles. And the number of moles of gas in each one is the same, yes. Molecules the same, moles the same, those go together. So 2 and 3 only, answer C. A temperature of 36 degrees represents twice as much kinetic energy as what? Okay, so it's a 36 degrees Celsius. What we have to do is change that to kelvins. We're going to add 273, and we're going to get 309. So that number, that's a better one for measuring kinetic energy. So this is twice as much as what? So we're going to divide this guy by 2. And so divide by 2, we get 154.5. And now we're going to turn it back into Celsius because all our answers there are Celsius. So I'm going to subtract 273. So minus 273, I'm going to get a negative number, negative 118.5. I said that wrong, negative 118.5 0.5 degrees Celsius. So there's an answer like that. There it is, negative 119. That's my answer. 78, a pressure of 745 mmHgs. Okay, well, I'm going to go ahead and set this up. Okay, what I had to do is go 760 millimeters of mercury, and we're trying to change it to atmospheres, 1 atm. So it's 745 divided by 760. So I know that's just a little bit less than 1. My answer is going to be 0.98, certainly not 0.56. And these guys are going the other way. Those are too big. So I just, without even calculating, I know it's 0.980 atmospheres. A pressure of the atmosphere at sea level will support a column of mercury that is how tall? Okay, so atmospheric pressure, 1 atm, that's going to be 760 millimeters of mercury. And that's what we mean is that, you know, if we had a column of mercury, that we would be able to support that in a barometer. Okay, what Celsius temperature is equivalent to 100 kelvins? Okay, so 100 Kelvin, I'm going to have to subtract 273 to get my degrees Celsius, and so I can tell that's going to be negative 173. Not too tough of a problem. Or you could use a calculator. 81, which of the following describes STP? Okay, 1 atmosphere and 0 Kelvin? No, that part's wrong. 1 torr? No, that part's wrong. 760 atmospheres? No, 1 atmosphere. 760 torr and 0 degrees Celsius. Okay, that is STP, answer D. And we would usually use that as 273 Kelvin. Okay, which of the following describes the volume of a gas sample as when the temperature is increased at constant pressure? So we're talking about volume, we're talking about temperature. If I increase the temperature, then the volume is going to get larger. We're talking about something like a balloon. Okay, if we heat up the balloon, it's going to get bigger and bigger and bigger. These are proportional to each other, so we're going to have this graph where the one goes up and they both go up. Okay, and which of the following is the pressure of a gas the greatest? I've got volume, I've got temperature. Well, if I decrease the volume, that would increase my pressure. And if I increase the temperature, that would increase my pressure. So I'm looking for high temperature, low volume. So high temperature, let's knock those two off. Okay, and then I want the smallest volume, so my answer is going to be B. That'll be the best one. 84, if the volume of a gas at 323 Kelvin is changed from 780 to 620 at constant pressure, what will the new temperature be? Okay, so I've got two volumes and I've got two temperatures and a volume, and so I have to work that out. So that's going to be V1 over T1 is equal to V2 over T2, and my temperatures are already in Kelvin, so that's good. So I'm saying that 780 milliliters, okay, is to 323 Kelvin, as X is to 600, I have this wrong, 780 to 620. Okay, so let me go back a little bit. Okay, so 780 milliliters Okay, 780 milliliters is to 323 Kelvin, as 620 milliliters is to what? And I know I'm going to get an answer that's smaller than 323. So now this is a math problem now that I've set it up. Okay, and I can see that, you know, this is getting smaller, so this is going to get smaller. I need an answer less than 323, so I can certainly knock that one off, and I can knock that one off. And so it's one of those other two answers. So if I just do, you know, cross multiply, so 780 times X is equal to 620 times 323. And to get X by itself, I'll divide both sides by 780. Okay, so I do 620 times 323 divided by 780. I get 256.74, and that's Kelvin. And so that's going to be my 257. 85, a sample of a gas with a volume of 700 milliliters and a pressure of 1 atmosphere is brought to a volume of 200 milliliters at constant temperature. What's the final pressure? So here I have volume and pressure and volume, so now I know I'm talking about P1V1 equals P2V2. So as my volume gets less, my pressure goes up, and I can say, well, that's going down, you know, about 3 times, so it should go up about 3 times. Okay, so I think my answer right there is D. The pressure is definitely going to go up. Certainly not going to be the same pressure. It's not going to go up just a little because this is going down 3.5 times, okay, and it's certainly not going to get less. So I know my answer is that. So I can plug and chug, but I know the answer is 3.5. 86. A gas at 780 mmHg with a volume of 2 liters is allowed to change its volume at constant temperature until the pressure is 600 mmHg. What's the new volume? So I've got a volume and I've got a pressure. Okay, so again, this is P1V1 equals P2V2. Okay, a gas at 760 with a volume of 2 is allowed to change until the pressure is 600. So I have 750 times 2 is equal to 600 times x. So to get x by itself, I'll divide both sides by 600. Okay, and not surprisingly, my volume is going to get a little bit larger because the pressure is going down, so the volume is a little bit larger. So a little bit larger than 2, so I know it's not 1.6. I know it's not going to stay at 2. Okay, probably not go all the way up to 15. I bet my answer is 2.5, but I'm going to calculate it real quick just to find out. So 750 times 2 divided by 600, yeah, 2.5 liters. Okay, 87. A constant volume of gas at 97.3 kilopascals and 275 Kelvin undergoes a change in pressure to 104 kilopascals. Okay, so what I have here, what's the new temperature of the gas? I think I said that wrong. I've got a pressure and a temperature and a pressure and a temperature. So this is P1 over T1 is equal to P2 over T2. So let's do it. So I have 97.3 kilopascals over 275 Kelvin. That's already Kelvin. So undergoes a pressure to 104 kilopascals over X. Now I'm gonna cross multiply. So 97.3 times X is equal to 275 times 104. And divide both sides by 97.3. That crosses out. So x equals this times this over this. Okay, so I'm going to, it's going to be just a little bit larger than 225. So, okay, that sounds, no, yes. I'm looking at the wrong question. Okay, here's my question up here. So it's a little bit larger than 225. So it won't stay at 225, and the other three are larger, so we have to calculate. So what do I have? 275 times 104 divided by 97.3. I get 293.9, so 294 is my answer. Okay, number 88. A gas at 25 degrees and 680 mmHgs occupies 345 milliliters. What is the volume of gas at STP? Okay, so if we see that, then we know that this is probably a P1V1 over T1 equals P2V2 over T2. Okay, so we'll say P1V1 over T1 equals P2V2 over T2. Okay, this is 25 degrees. We're going to change that to 298 Kelvin. Okay, it doesn't matter about the other units. So P1 is 680. I'm going to change colors. Okay, to help it easy. So it's going to be 680 millimeters of mercury times the volume, which is 345 milliliters, all over 298 Kelvin, is equal to, now at STP, okay, so the new pressure in STP will be 760 millimeters of mercury. And the volume is what we're looking for, and the new temperature is 273 Kelvin. So now we just have to solve this. It's at 6:0. Okay, and I'm going to take a minute to do that. So I'm running out of room. So I'm going to cross multiply. So I have 680 times 345 times 273. So I did this one, and this one, equals 298 times 760 times x. So to get x by itself, I'm going to do this one, divided by this one, divided by this one. And when I do that, I get 282.78. So 283 looks like my answer, answer A. Okay, 89. 1.22 liters of a gas at 298, 750 undergoes a change in pressure and temperature to 323 and 710. What's the new volume? So this is the same kind of problem. P1 V1 over T1 equals P2 V2 over T2. But the difference this time is they're actually telling us the numbers. Okay, so P1, so I have 750 mmHgs times 1.22 liters divided by 298 Kelvin is equal to, P is 710 millimeters of mercury times the new volume is what we're looking for over 323. Okay, so they're telling us everything. So I'm going to do this times this times this divided by this, and I'm just going to work out the answer and write it down. So 750 times 1.22 times 323 divided by 298 equals, divided by 710 equals, I get 1.396. So 1.40 would be my answer. Okay, 90. What volume of 27.6 grams of SO2 occupy at a pressure of 97.3 kilopascals and a temperature of 38 degrees Celsius? Okay, I'm going to need some room. So the molar mass is 64.1. The fact that we're talking about grams and moles, I know that this is PV equals nRT. And we are looking for volume, so volume equals nRT over P. Okay, so that's my problem, nRT over P. But the first thing I need N. So I have 27.6 grams of SO2, and it says that there are 64.1 grams for 1 mole of SO2. So my number of moles is 27.6 divided by 64.1. I get 0.43, so 0.431. That's how many moles I have. Okay, that's now I need R. I know R is 0.0821 liter atmospheres per mole Kelvin. My temperature, 38 degrees, 38 plus 273, that is 311 Kelvin. Okay, divided by P. P is 97.3 kilopascals, and I'm going to have to divide that by 101.3 kilopascals to put it into atmospheres. That's just a little bit less than 101.3, so I'm not surprised my atmospheres is 0.9605 atmospheres. So now I just have to work this out, and that's going to come out to be my volume. Okay, so 0.431 times 0.0821 times 311 divided by 0.9605. I get 11.457, and that's liters. So 11.5, 11.4, that's pretty close right there. That's my best bet. Okay, 91. A 24 milliliter sample at 100 degrees and 755 mmHgs is found to have a mass of 1.22 grams. What's the molar mass? Okay, now molar mass is grams per mole, so I have to find the grams, and I have to find the moles. And I know the grams. The grams is 1.12 grams, so I need to find moles. If I'm doing moles, then I'm really doing PV equals nRT. And what I'm actually is N equals PV over RT. So I'm just going to substitute in my values. Okay, my pressure is 755 mmHgs. I have to change that into atmospheres by dividing by 760. So that comes out to be 0.993 atmospheres. Okay, V is 240 milliliters, which is 0.24 liters. Okay, R we know is 0.0821 liter atmospheres per mole Kelvin. And 100 degrees Celsius, we're going to change that to 373 Kelvin. So here's the numbers I need, and I'm going to do it real quick. So 0.993 times 0.24 equals, divided by 0.0821 equals, divided by 373 equals, and I get 0.00778. Okay, that's how many moles. So I'm going to put that down here. So 0.00778. So 1.12 divided by 0.00778, that comes out to be 143.9. So that is really close to 144. That's my answer. So when I do those two, I get 143.95 grams per mole. So 144. Okay, last question. A sample of a gas at STP has a volume of 1 liter. How many moles of this gas are contained in this sample? How many moles of this gas? A sample of a gas at STP has a volume of 1 liter. How many moles of gas? Okay, it's talking about moles, so we know that this is PV equals nRT. And like the one before, then N is going to equal PV over RT. Okay, we're talking about STP, so the P is 1 ATM. Okay, the volume is 1 liter. And R is 0.0821. And the temperature is STP, so that's 273 Kelvin. So I do 1 times 1, which is 1, divided by 0.0821, and divided by 273, I get 0.0446 moles. So 0.446, there it is, answer A. And that is the last portion of this test.